Hi, I'm Katja Barthelmi. I'm a PhD student in the group of Professor Holleitner, and we're here in the Center for Nanotechnologies and Nanomaterials of the Technical University of Munich. And it's located in Garching near Munich. Today I will show you how we generate single photon emitters in a monolayer of MoS2 and how we study this material in our labs. This is a 360-degree video, so if you want to look around, you can do that while clicking the mouse. And due to the corona crisis, we have to wear masks inside the hallways. So let's go to the first lab. We're here in our Exfoliation Lab. That's where we fabricate the samples. After the fabrication, we bombard the sample with a Helium-ion microscope. And after that, we will show you how we study this material. In this Exfoliation Lab, we mechanically cleave the material and make thinner layers. And we do that in a glass box. Inside we have a nitrogen atmosphere to protect the materials from oxygen, and you can see the bulk MoS2 in this round box. And since the layers in this crystal are bound together with van der Waals forces, it's easy to cleave the layers mechanically with the tape you see next to the box. And now we get inside the glass box, and I will show you how we do the exfoliation. We have the bulk material here, and we put it onto the sticky tape. And with the mechanical force, we can pull layers from each other and create thinner and thinner layers. So we take the tape and pull them apart like this. And we transfer a bit of the material onto PDMS, which is a rubbery material, the same that is here. And we search under a microscope for monolayers. As I just said, we search for single layers, monolayers of MoS2 underneath this microscope. That is the one that you just saw from inside the glass box. And here you can see the microscope image of that. This is a kind of a thicker bulk piece of MoS2, and here on the bottom of it you can see the monolayer. And when we found a monolayer of MoS2, we encapsulated it with a hexagonal boron nitride to protect it from ambient gases like oxygen. And we do that we stack this heterostack with the PC method. So for this, we use a small PDMS square, and we place PC, it's a polycarbonate, on top. And so we create a stamp, and with that stamp, we pick up the three layers, the hexagonal boron nitride, the monolayer of MoS2, and another hexagonal boron nitride, and we place it in the end onto a silicon substrate. And we do that at the stacking setup here. So we place the PC stamp on the glass slide on the top stage, and on the bottom we place the layers. And then we pick up the single layers or the 3 layers, and then we place it on a silicon substrate that you can see here. And in the end, the sample looks like this here. We have the hexagonal bornitride underneath. This is the monolayer of MoS2. And we place another hexagonal bornitride layer on top. And on the right here, you can see a schematic figure or an image of the fabricated sample. And we bombard it with helium ions that come from a helium-ion microscope. And that is located in another lab. So let's check it out now.
Thanks, Katja. My name is Alexander Hötger, and I'm also a PhD student in a group of Alexander Holleitner. And this is the focused ion beam lab. And I'm going to show you the helium-ion microscope behind me. Just follow me. So, this is the helium-ion microscope. What we can see here is the vacuum chamber where we load our samples in. Also the airlock. And yes, this is the user interface we're dealing with. And here we're designing our patterns in order to shoot into our 2D materials. So to visualize that, I have a couple of slides for you here. So what we can see here is the pattern that we irradiate our samples with. So these are single shots, and they are done because we want to have some statistics on how probable it is to get this single emission that we see in our samples. So for pristine MoS2, we don't have any one of these sharp lines appearing in the photoluminescence spectra. However, if we irradiate the sample with very low dose, we see a single emission of a very sharp peak coming up, and with high dose, we actually see more quantum images popping up. And we also have G2 measurements, which give the quantum emission also the property that it is actually a single photon emitter. So here we can also compare our single photon emission with other quantum emitters and defects in the field, and we can see here the lateral position against the axial position, which is very high in lateral and also in axial position for the helium ion, because we can focus the helium ion beam quite good and down to a resolution below 1 nanometer. And for other single emitters, for example, in NV color centers in NV centers, and also in HBN, some defect emission, they have quite high or quite low precision axial and also lateral, and therefore we have an advantage with our helium ions, which generate really atomistic small defects, which we attribute to vacancies of sulfur in the molybdenum disulfide monolayer. So now we move on to the poster here, which is nearby the HIM. And there we see the principle of the HIM with a tungsten tip, which is surrounded by helium gas, and the helium gas gets ionized at the very tip, which you can also see here in this small inset. In this panel, we apply a 30 kilo electron volts onto the tip in order to accelerate the ionized helium ions, and these helium ions are then accelerated through the whole path of the helium-ion microscope, deflected also with magnetic lenses, and focused finally onto the sample. And detected eventually at the Eberhard-Thorny detector are then electrons which are scattered at the surface. And now down here, we see the secondary electron formation for different sources. For example, the gallium ions with also accelerated with 30 kilo electron volts, electrons in a SEM, and also finally the helium ions. And what we can see easily that in the substrate, the distribution of the secondary electrons is quite high in lateral position for gallium and also electrons won't penetrate that deep. However, the helium ions are penetrating quite deep into the substrate, leaving us with less backscattered secondary electrons, which are coming again to the surface where our monolayer of MoS2 is located, and therefore reducing the lateral position of the helium ion or the bombardment, and also therefore increasing the precision, of course. So that's why we're using helium ions. And now we move on to the photoluminescence measurements and also some other measurements which we can do in optical setups upstairs. Just follow me.
Hi, welcome to the Optical Spectroscopy Lab, where we characterize our 2D materials. My name is Katie and I'm going to show you the lab. Thanks, Sandy.
See you later.
Follow me. So this is our measurement lab where we do low temperature and B-field dependent measurements, PL measurements. Sorry for the noise, that's the pump that's keeping the cryostat cool. So this is our cryostat where we cool our sample using helium down to way below room temperature, so roughly 1.7 Kelvin at the moment. And just to show you, we have 0 Tesla, so the B-field is off at the moment. So let's start from the beginning, which is on this optical table right here. We have 3 lasers, 514 nanometers, 637, and 780 nanometers. So depending on the measurement that we do, we can use 3 different excitation energies. And these lasers are then using these mirrors centered into this fiber coupler. So these fibers are these yellow lines that you can see there, 1 for each laser. So this whole system is fiber coupled. Over here we have a power wheel so that we can kind of use smaller excitation powers so that we don't break our sample, or don't break our sample. So the fibers are then, they go up here all the way over the room into our optical head, which is everything that you can see here mounted on top of the cryostat. The laser is coming in through this way, through the excitation port, so through this fiber. And then it goes down through all sorts of optics. Using a dichroic mirror, it goes down onto the sample, which is mounted into this cryo down here. And then the PL signal, for example, goes back up, and then using this mirror over here is put into the detection path, which is this fiber, which then goes into a different room, into our spectrometer. The things that are quite nice about this setup is that we have a low temperature objective, which is in the stick, and a CCD camera on top with a light source so that we can actually image the sample so that we're at the right area. So just to quickly show it in the scheme, so it's maybe a bit more clear. So this is the CCD camera, and this is the optical head that I was talking about that is mounted on top of the cryostat, which is this black box down here. We have these 3 lasers that are excited, or that excite, one of each, that excite the sample. And it goes down through this low temperature objective, which you can see in this image over here, where we have this piezo stack X, Y, Z, so that we can move it in all 3 directions. And then, as I mentioned, the objective collects the signal, and then it goes into the detection port. So the nice thing about the setup is that we can adjust it in any way that we want, depending on the measurement. So we can use lambda plates, for example, lambda fourth or lambda half plates, to also do polarization dependent PL. And also naturally we can use our superconducting magnet, which has a range from -9 to 9 Tesla, which can be swept in this range to do magnetic dependent PL measurements to determine G factors and the Zeeman splitting and things like that. So this is our measurement setup. Thank you so much for joining our lab tour. And we are going to leave a link in the description for our group's homepage in case you have any further questions. and see you soon. Thank you.
Bye.
Bye.
Bye.